Okay, so welcome to this final lecture. Uh, okay, so let's see. Can you hear me? I'm not able to. Okay, so let's get started with today's lecture. This is going to be the final TA session for this course and this year. So today is 20th October and the final TA session for the NPTEL course Applied Linear Algebra for Signal Processing, Data Analytics and Machine Learning, offered by Professor Aditya Jagannatham from IIT Kanpur. Again, a quick introduction about myself. My name is Yashvanth, and I'm presently a PMRF PhD research student at the Indian Institute of Science, Bangalore. And I'm also advised by Professor Chandramurthy, who is also with the Department of EC at IISc. My broad research interests lie in signal processing and applications in wireless communications, while I currently focus on intelligent reflecting surfaces for 5G and beyond wireless com. You can always contact me in this email ID, and you can know more about me by navigating to this web page. Okay, so as I had promised last time, the topics that we are going to cover today is in some sense going to um, summarize all the key topics from linear algebra and see where they come together and play as solutions, a role of solutions in variety of research, everyday life applications. So this part one of today's class will be on dealing with radar applications. In particular, about there was one particular lecture where professor had detailedly explained about the angle of arrival estimation using music and etc. So today I'm going to talk about that in little detail by explaining exactly in what kind of applications can we use these linear algebraic concepts. So what I've planned for today is basically to go over the research papers that have been published by several well-known people in the community in the engineering field. So the first paper that I'm going to talk about today is titled as follows. So incidentally, this is one of the papers that I myself co-authored. So my name is Yashwant, and this was a work that I did as a part of my project in my BTech during my BTech. So and it and this paper was got published in 2021 in the Journal of Progress in Electromagnetics Research. C. Okay, so the paper title is very important. The paper title is important because that's gonna essentially set the stage for this particular piece of work. So the paper is titled "On the Role of Time Frequency Analysis for Joint DOD/DOA Estimation for Bistatic MIMO Radars." Okay, so essentially, what is important is, uh, okay, did I start recording? Just a minute. Okay, recording is on. Okay, so essentially, this paper is about bistatic MIMO radar. Okay, so that is the first. That is a broad system setup that we are considering, and in this system, what we are interested is joint direction of departure and direction of arrival estimation. Okay, and in turn, how to solve this problem of joint DOD/DO estimation using time frequency analysis. Okay, that is basically the primary goal of this particular paper. Okay, so I have okay, so this basically is abstract. So abstract basically tells what is the gist of this paper. Okay, so let me without ado let's get started. So there is some introduction to this paper where it talks about the prior existing solutions in this particular system of bistatic MIMO radar. Okay, so let me directly jump into the bistatic MIMO radar. What is a bistatic MIMO radar and how will the modeling of signal equations look like? Okay, so it's very simple. There is a transmitter, there's a receiver. Okay, so basically, what is a radar? First of all, we need to understand what is a radar, what a radar is. So radar basically is basically okay. So there is the full form is also there here. Radio detection and ranging is basically the abbreviation, the full form of a radar. Basically, what a radar does is it will try to sense for detect for any targets that is present in the environment. For example, for military applications, one particular node would want to sense the other presence of other objects which are present in the environment, which may be otherwise, through naked eyes you may not be able to sense. One reason could be that it's very far away from our vision, but we are not able to detect the presence of the target. Okay, target is something that is of interest. Okay, so that is of interest whether there's a target or not. Okay, so radar, what it does is, the main principle of a radar is that, like something like this. Okay, there is a transmit array. Okay, so that means what it does is, there is the transmit array will send a waveform. Okay, the waveform will go, and if there is a target, it hits the waveform, and then it reflects back, and the reflection is collected at something called the receiver array. Okay, now the receiver array has the knowledge of the transmitted pulse, the pulse of the waveform. Okay, now depending on the difference between the pulse that the received array got and the pulse that has been sent out from the transmitted array, the receiver array will then try to compute or determine whether there was a target in the system or not. If there was a target, what happens is, the transmit signal go, hit the target, reflect back to the receiver. If there were no target, it would have the reflection will not come back to the receiver array. That's all. As simple as that. If the reflection comes back to the receiver array, that means that there was a target. If the reflection does not come to the receiver array, that means there was no target in the environment. So that is how a radar basically tries to detect for the presence of a target. Okay, let's say there is a target that is already present. Now then I want to know where exactly is the target present in the environment, right? So for example, you see this particular picture here. There's something called the kth target. So for assume, just let's assume that there's one target. So this is one target. Okay, what are the characteristics or the parameters that you can associate with this target with respect to the transmit and receive array? The directions. For example, you see, with respect to the transmit array, this target is located at angle theta k with respect to with respect to the normal of the transmit array. Similarly, with respect to the receiver array, this target is located at a distance of that makes phi k as an angle phi k with respect to the normal to the receiver. So essentially, if I can somehow find both theta k and phi k, you are able to you will be knowing in which basically along which axis, in which direction is my target exactly present. Now I can also I should also know the distance, how to find this distance. Okay, if I know this angle and if I compute the distance, then I can exactly locate where the target is present in the environment. And these are the functionalities that one can perform by having a radar in the system. Okay, so now we have understood what a radar is. What is bistatic MIMO radar? Okay, so basically bistatic means the transmit array and the receive array will not be located together. Okay, they will be located somewhere else. For example, a transmit array, there could be a transmit array here, and the receive array could be somewhere very far from the transmit array. Okay, so that the pulse goes, it hits the target, and then it goes back to the receiver like this. Okay, this is called a bistatic MIMO radar. Okay, similarly, what is a monostatic MIMO radar? Means transmitter is sitting here, receiver is again sitting at the same place. Both are located at the same location. Okay, that is called a monostatic radar. That is what it does is, transmitter will impinge this, will emit a signal. It will go to a target. It gets reflected and comes back in the same path as it had traveled in the initial transmission. Okay, this is called a monostatic radar. Whereas whenever the transmitter and receiver are located not at the same location, that is, they call it non-co-located. Okay, if it is co-located, means it's monostatic radar. If it's non-co-located, then it's called bistatic radar. Okay, and there's something called multistatic radar, where you have just multistatic is something like you have one transmitter here. There'll be some target. It goes and it reflects back to multiple receivers. Okay, there are multiple receivers. Okay, receiver, which everything is located at different distances. And then what happens is, each of these receivers will get the information from the target, and all these receivers will jointly process the information to come to a conclusion whether there was a target or not. If there was a target, where is the target, at what is the angle with angle that this particular target is making with respect to the transmitter and all the receivers. What is the distance at which this target is located with respect to the transmitter and receiver, and all these functionalities one can compute. Okay, so that is basically the first part of what is a bistatic radar. Now, what is MIMO radar? Bistatic MIMO. So MIMO is we have been looking at this terminology for quite a while now. So bistatic MIMO just tells that the transmitter has multiple antennas, the receiver also has multiple antennas. So it's a multiple input system. Input meaning the transmitter has multiple antennas, so there are multiple inputs to the channel in order to sense whether there's a target or not. And then once the target target reflects the impinging signal from the transmitter, the receiver array will also have multiple antennas in order to get multiple outputs. So it's a multiple input, multiple output system. That's why it's called MIMO radar. So the entire that basically comprises what is called as a bistatic MIMO radar. Okay, so now in general, you would not want your target what is it called? In general, you don't want your radar. You don't want to design your radar only to detect the presence of one particular target. You may want to detect for multiple targets in the environment, right? So that way, if you see, you may not be able to. You may not want to design a radar only for detecting one target. You should be able to accommodate detecting multiple targets in the environment, and each with its own signature, meaning each with its own properties. Okay, so that's where, so this particular paper or this particular work that I'm going to take today, discuss today, it has the following problem. The problem is that there are P targets in the environment, capital P number of targets in the environment. Okay, the goal is to find the DOD and the DOA of each target. Okay, let me draw a diagram. Okay, before let me draw a diagram of what is the exact problem. Okay, there's a problem. Is the problem which we have to solve is like this. So there is a transmit array. Okay, for example, there's a transmitter array or transmitter array. Yeah, transmitter array, and there is a receiver array. Okay, so transmitter array has NT antennas, for example. It has NT antennas, and receiver has NR antennas. Okay. Let's say there are P targets. Okay, let's say target 1 is here, target 2 is here, target 3 is here, and so on till there are P targets. Okay, this is target 1, 2, 3, and so on till capital P. Fine. And then now what happens is your transmitted signal will go to first target, gets reflected, and goes to receiver. Then for the second target, the same signal goes to second. The transmit array will emit a signal. That signal will go to the second target, and then it will come back to the receiver array. Okay. Then it goes to third target, again receiver array. Then fourth target, PH target, then receiver array. Now each of it. Okay, 1 minute. Each of it will make one angle, right? For example, now I draw a particular reference, okay, at the normals. Okay, now you see this angle made with the normal of the transmitter array is called theta1. That is this is called the direction of departure, because that is basically the angle at which a signal is getting departed from the transmitter array and it's moving towards the target. So this is called the direction of departure. Okay, so theta1 is the direction of departure or the angle of departure from the transmitter array towards the target one, towards the first target. Theta2 is the DOD of the second target. Theta3 is the DOD corresponding to the third target, and theta P is the DOD or the direction of departure corresponding to the pth target. Similarly, after getting reflected at each of the targets, all of them will arrive at the receiver with respect to some angle. Okay, so for example, first target will come with phi1, that is the direction of arrival. Direction of arrival. Okay, or they call DOA. This is called DOD. It's called DOD. Fine. So the first target will make an angle phi1 with respect to the receive antenna. With all respect to all the receive antennas. Remember when we studied even in our previous classes, we assumed that the targets are present in the far field location, right? That meaning that the distance between targets and the antennas are very, very large. That the signal, you can assume that all the rays, the angle made by the target or the source with all the antennas are the same. That's what even I'm assuming here. This phi1 is the angle made by the first target with respect to any antenna at the receiver. Okay. Similarly, the DOA of the second target is phi2. Similarly, DOA of the third target is phi3, and DOA of the fifth target is phi-p. Okay. Now, what you do is you send transmit signal X. Is a transmitter signal. Okay. Now you get some receive signal Y. Now the problem okay, given Y, that is after you observe given Y, find theta 1 comma phi 1, okay, theta 2 comma phi 2, and so on till theta p comma phi p. Okay, that is the problem. That is, you need to estimate DOD and DOA of all the targets, of all the P targets, given the observations, which is denoted by the letter Y. And this is basically the problem of joint DOD DOA estimation for bistatic MIMO radar. Okay, and now the specific solution that we are going to use in this particular paper is something called the time frequency analysis. Some of you would have heard about it, that it's a fundamental property that some of you who would have taken signals and systems course will be knowing, that if you take any signal in the time domain and take its Fourier transform, it'll have its corresponding frequency domain. For example, let me also explain motivation for time frequency analysis. That is also very important. Okay, or it's called motivation for TF, or short is called TF, for time frequency analysis. Okay, so basically it's a fundamental property that you cannot localize the signal in both time and frequency domains simultaneously. Okay, so for example, some of you will recollect this very important fact. For example, if my time domain signal x of t is equal to sine 2 pi t. Okay, so how does it look like? In time domain, it looks something like this. Okay, but I'm not gonna put any restriction on what is t. T ranges from all the way from minus infinity to plus infinity. Okay, means it's always existing, even in the future, the present, the past, present, and future, all time zone. This continuous time signal exists. Okay, that is called x of t. Okay, this is what it is, not time limited signal. Okay, but if you compute the Fourier transform x of f, will be, I'm just giving an example. Okay, this sine 2 pi t, what is the frequency? Is nothing but 1 hertz. Okay, so if you compute the Fourier transform of this particular function sine 2 pi t, you can show that the amplitude of your Fourier transform, amplitude of x of f, will be like this. It will have two peaks in -1 and +1. Okay, everywhere else is 0. Okay, basically what does it tell? In the time domain, the signal was infinitely limited. It's not time limited, but the frequency, it's limited in frequency. That is exactly only a 2 frequency. It is equal to it has a non-zero value. Everywhere else it has a 0 value. So it is localized in frequency. Localized means it's just it's confined. The non-zero value is confined within a particular interval. Here it's exactly non-zero is only 2 points, -1 and 1. Everyone else it's 0. So it's localized in frequency domain, but it is not localized in time domain because this particular signal exists for all time. Not localized in time domain. Okay. And now the thing is that if I somehow truncate my x of t, naming that alternatively, consider the following signal. Okay, x of t equal to, let's say, same signal sine 2 pi t, but now I do a change that now t lies only between -10 and 10, else it is 0 everywhere else. Then you can show that x of t is same as like that, but it will be something like this. Okay, something like this. Let's say this is 1, -10, and this is -10. Everywhere else it is 0. Okay, it's strictly time limited, so it is localized in time domain. Okay, so how do you get this signal basically? So let me call this as x t of t, or x dash of t. Okay, x dash of t is equal to sine 2 pi t. How do you get this signal? Essentially very simple. You can obtain x dash of t from x of t as x of t times a window function, w of t. Basically put a rectangular window over this x of t function with window length equal to -10 to 10, such that the window is such that it is 1 between -10 and 10, 0 in any other interval. Then basically if you multiply this window function to this original x of t, you will get x dash of t. Correct? So basically that is how. So in the frequency domain, what does it correspond to? Let me first draw the w. How does w look like? Where w of t is something like this. W of t is a signal from -10 to +10 t. It's called a window function, or something it's called rectangular window of amplitude 1. Okay, if x dash of t is equal to x of t into w of t, it's a fundamental fact that in Fourier domain they will come as convolution. Okay, then in Fourier domain, x dash of f equal to x of f convolution w of f. Okay, we know x of f. X of f is precisely this quantity. But what is w of f? You can show that the Fourier transform of this rectangular window function is given by something like this. It's something like a sinc function. Okay, w of f. Of course, there is no negative. Okay, so I should be a bit careful. Okay, it's like a sinc function. It's exactly a sinc function. Okay, with aspect of function of f. Sinc, if you remember what is the expression w of f is nothing but sinc t, which is nothing but sinc f. Sinc f, which is nothing but sine 2 pi f. Sorry, sine pi f by pi f. That is basically the definition of sinc f. So what I'm trying to say is this is not localized because this extends from -infinity to +infinity, f from -infinity to +infinity. Therefore, now if you convolve w of f and x of f, okay, if you plot the amplitude spectrum of mod of x dash of f, you will start to see something like this. There is a peak here, there's a peak here around -1 and +1, but you're going to have a lot of such things, a lot of sync ripples. And this will keep on continuing for all ranges from -infinity to +infinity. This is not localized in frequency domain. Okay, so what does it say? You have been able to localize the signal in time domain by multiplying with a window function, but the same window function, because of multiplication, creates a ripple kind of a behavior in the frequency domain, because this window function in its Fourier domain has the support, or the duration of the signal in the Fourier domain is all the way from -infinity to +infinity. So your Fourier transform is no longer band limited. They call this as band limited. Whenever the Fourier transform is limited within a bandwidth or a limited in a given signal interval, it's called band limited. This signal is not band limited. Okay, not band limited. Okay, so this is precisely the uncertainty. I mean, this is precisely the trade-off. Okay, one can think about in time frequency localization. You cannot localize a particular signal in both time and frequency domain simultaneously. Simultaneous is very important. See, here you are able to localize in time, but not in frequency. But here you are able to localize in frequency, but not in time. Simultaneously, you cannot try to localize in both time and frequency domains. So this is basically a fundamental, trade-off in signal processing that people end up with. So if they want to know, for example, at t equal to 1 second, at this moment, what is the exact frequency of this signal? If someone asks this question, people cannot answer. People tell, okay, I don't want to answer that question because I don't know the answer, because you cannot simultaneously localize. But people can alternately do what they can do is, okay, given an interval, okay, in 1 hour of time, what was the frequency, average frequency content signal? People can answer that. Okay, so that's why people wanted to get precise answers for the first question, namely that what is the frequency content at a given time. So that basically led to a separate branch of signal processing called time frequency signal processing. Okay, and that had lot of developments today. It is almost a very richly developed field today, and precisely I'm going to use that tool today for solving the DOD TO estimation problem. For the one reason, why do we need time frequency analysis? The reason being that in radar systems, these targets can potentially be in movement. Okay, if these targets keep moving, there is associated with change in Doppler shift also, because we all know, right? Whenever there's a target, whenever there's a source that keeps moving, the frequency that we measure at the frequency that receive array will no longer be the true frequency, but it will be perturbed by a Doppler frequency. And this Doppler frequency could be a function of the velocity with which this particular object moves. Fine. So in many cases, we may be interested in estimating the Doppler frequency also, which will tell about how this particular target is maneuvering over about a particular fixed position. Okay, so essentially the fact I'm trying to say is this Doppler can potentially try to degrade the properties of the signal if you don't account for, and that's why I'm going to account for, I'm going to use the time frequency analysis in order to separate out the different Doppler frequencies exhibited at different times, different time of instance of time. Okay, I'll explain about all these things. So that is basically the motivation behind using a time frequency based framework in order to solve this problem. Fine. So let me go over this paper now. Okay, so basically I have set up the system. It is a bistatic MIMO radar system. Now we will get into the signal model. Okay, so basically what happens is, okay, again I'll go back to my picture. I will write down the signal and then we will go back to this paper. Okay, you see, okay, maybe I should include a new page. Okay. Okay, now let us see the signal model due to the first target. Okay, so what happens? The transmit array will basically send out a signal, go to the first target, and then that will come to the receive array. Okay, so I'm going to write that basically this as follows. So y1, which is basically the signal received at the array from the first target, I can write this as a nr of what is this? Phi1. It is a direction of variable is Phi1. Okay, this is an nr cross 1 vector. Okay, this is also NR cross 1 vector. If you recall, NR of phi 1 is nothing but the array response vector corresponding to direction phi1. Okay, times ANT of theta 1 Hermitian. This is nothing but 1 cross NT. Okay, this is 1 cross NT. And ANT of theta 1 is nothing but the array steering response vector at the transmitter array with the direction of departure theta 1. Okay, so this is the array response vector of length NT cross 1. Okay, with constructed at the angle theta 1, but it comes with a Hermitian. That is why it's 1 cross NT. Okay, this Hermitian, you can think about why there should be a Hermitian is because, see, if you have NT cross 1, I cannot multiply NR cross 1 and NT cross 1. I cannot multiply two vectors just like that. But if I'm going to make 1 cross NT, then it will become, this multiplication becomes defined. NR cross 1 times 1 cross NT will become an NR cross NT matrix. Oh, sorry. Yes, it's an NR cross NT matrix. It's NR cross NT matrix. Okay, but there's one more small thing. Namely that this is not it. This is not it. There is also an associated data that the information, the pulse that I will transmit from the data from the transmitter array, that will be NT cross 1. Okay, so this becomes NR cross 1. Fine. So basically, what I'm saying is every antenna will have, so basically this will be something like this. There'll be first antenna 1, antenna 2, antenna 3, antenna 4, and so on till antenna NT. The first antenna will send out S1, S2, and so on till SNT. Okay, this is the data. So then you can collect all these vector S is nothing but S1, S2, and so on till SNT. Okay, in some sense, this is what is called a channel. Okay, this is what is called a channel. So basically, you see here, this is like your data. This entire space is like a channel, and this is like your receiver. It's like that. You can bring an analogy between this problem and the problem which professor had described as part of MIMO wireless communications in the lectures. But there's one more thing in this particular equation. See, each of the targets will also impose a particular reflection loss, right? So for example, it's getting reflected, right? So there'll be reflection coefficient associated with each of the targets. Okay, I'm gonna call that as, with respect to first target, as gamma 1, which is a 1/1 scalar, and gamma 1 is a complex number with the property that modulus of gamma 1 is less than or equal to 1. That is the property of any reflection coefficient. Okay, the complex number such that the modulus, the magnitude of the number gamma 1 is at most equal to unity 1. Okay, so this is basically the received signal due to the first target. Okay, therefore the received signal due to all targets, due to all p targets, there are p targets is nothing but sum of all of them. So y is equal to summation of yi from I equal to 1 to p is precisely equal to summation over gamma I times ANR of phi times ANT of theta I Hermitian times S. S is independent of target number, so because it is getting transmitted from the transmitter, and I ranges from 1 to p. Okay, this you can actually show that you can write this as ANR times gamma times ANT times S, where ANT Hermitian, where ANR is nothing but the matrix comprising all the array steering response vectors at the receiver. So ANR of phi1, ANR of phi2, and so on till ANR of phi p. This is a matrix of size NR cross p, and A and T is similarly equal to A and T of phi1, theta 1, A and T of theta 2, and so on till A and T of theta p. This much NT cross P, and your gamma matrix is nothing but diagonal matrix comprised with diagonal matrix all equal to reflection coefficients of all the P targets. It is of dimension cross P. Okay, and this S matrix is the same as the data vector which we have been using everywhere. Okay, so you can write down the received signal at the array due to the contribution from all the P targets as something like equation 1. A and R times gamma times A and T Hermitian times S. That is precisely what I'm starting in this paper. Here. Where is it? Huh. You see here? That is precisely what I'm talking. Now, in addition, if I let T such pulses, so let's say the transmitter transmits T such pulses, then this matrix S, I mean, then what happens is you can define your, you know, so basically what happened, you had, then you can find xi of T equal to ANR, or I'm calling ANR as AR because it just received, times gamma times AT times SI. This is what we saw in the notes. You can now, you collect all x's together. Okay, this xi's together. So this is x1, x2, and so on till x capital T. That is, I'm sending T such snapshots, T such pulses I'm transmitting at the transmitter, and the receiver also gets T received snapshots. This is equal to AR gamma AT times S1, S2, and so on till ST. Okay, now call this as capital S and call this as capital X, and that is precisely your equation 1. Okay, also you can always add noise. Correct? Noise is inevitable. Any communication system will have a noise added to it. That's why if you see the x of T dimension is nothing but NR cross T, where each column represents the received signal at the receiver due to one snapshot, due to one transmission. Like that, due to T transmission, every transmission will go and hit the pulses, hit the targets, and then come back to the receiver. Okay, this is basically your signal model. Okay, this is how you write down the received signal at the radar. Where what is this? Where basically your AT will comprise. See, okay, let's do very step by very carefully. Let's go through again. Where AR, okay, just clearly follow me. AR is a matrix given by this particular equation 3. See, I'm highlighting here. Sorry. This the equation below equation 3. I'm highlighting here. AR is a which is a collection of all the array response vectors at the receiver due to P targets. Where AR of Phi1 is the array vector at Phi1. AR of Phi2 is the array vector at Phi2, constructed the angle Phi2. AR of PP is the angle vector, array vector at PP. And in turn, how is the structure of AR? It's given in equation 3. Okay, it's given like this. Very similar to, I'm assuming a uniform linear array at both the transmitter and the receiver. And professor had already told this in the class. Okay, similarly, you define your capital AT matrix as something like this. Collection of all the array steering response vectors due to the P targets. And in turn, the array vector is given by this equation 2 for at the transmitter. Okay, and as I told you, this gamma of T, it collects that, it's a diag of gamma of T means that it collects all the reflection coefficients along the diagonal entries. Okay, the small gamma of T is a vector. So diag of a vector means it's a matrix, it's a diagonal matrix, the diagonal elements given by the elements in the vector gamma of T. That is the meaning of this notation. Okay, so essentially then what I can do is very important. Okay, now how should I choose my S? S is a matrix now. It's a NT cross S matrix, right? How should I choose my S? That is precisely the engineering behind radar. What they do is they design their capital S matrix. This is called a transmit waveform because it's essentially data that waveform that the transmitter sends out in the air, right? So they ensure that the kind of a waveform they design is something that satisfies this condition S Hermitian equal to identity. Or in other words, the matrix S is should satisfy the property that it is the rows are orthogonal to each other. S Hermitian equal to identity means the rows of the matrix S must be orthonormal, in fact, because equal to identity. Okay, they are the rows of the matrix S must be orthonormal. You have to design your waveform like that. Okay, now once you design your waveform, once you ensure that the data that you transmit out of the transmitter satisfies this condition, what you can do is you can do something called matched filtering at the receiver. So what you do is you get this x of t at the receiver, you post multiply on both sides with S Hermitian. Okay, once you do post multiply with S Hermitian, the data part will have S times S Hermitian, that will go to identity matrix. Okay, and noise n of t will get multiplied by n of t times S Hermitian. That will be some other noise, resultant noise, which I call it as Z of t in equation 4. And x of t times S Hermitian, I call it as y of t. Okay, and very, very important, very, very important. See, S is a matrix of size. What is a matrix? S is a matrix of size nt cross t. Okay, if I want this matrix to be matrix such that all the rows are orthonormal, you should have t to be at least greater than nt. Okay, very, very important. The number of snapshots, the number of pilot transmission, for example, you may, for a want of a better name, the number of pilot transmissions that you have to do must be at least equal to the number of transmit antennas that you have in the transmitter. Okay, why this is important? Because only then can you ensure that all the rows can become orthonormal for the matrix S. Okay, so the minimum number of transmission you should do is what? T is greater than or equal to NT, or set T equal to NT minimum. Okay, so you need to at least do these many transmissions in order to preserve the property that S Hermitian equal to identity. Okay, then what happens is your x of t times S Hermitian is of size what? NR cross t and t cross nt. Okay, then the total is NR cross nt. That is basically your y of t. Okay, and Z of t is basically the filtered noise. After performing matched filtering, the resultant noise, the residual noise that remains is your Z of t. Now, very important, you can show that this gamma of t is basically a diagonal matrix. Okay, now by using the properties of matrix theory or linear algebra or whatever, you can vectorize this equation. What is vectorization? Okay, suppose I have a matrix like this: a1, a2, a3, a4, a5, a6, a7, a8, a9. Okay, if I have a matrix like this, it's a 3 by 3 matrix. The vectorized version of this matrix is given as like this: a1, a4, a7, a2, a5, a8, a3, a6, a9. Basically, take all the columns. Sorry. Okay, a1, a2, a3, a4, a5, a6, a7, a8, a9. Okay, this is basically the first column vector a1 or a. Okay, this is the second column vector AB. This is the third column vector AC. The vectorized version of this matrix nothing but take AA, then stack below AB and stack below AC. Okay, so this was a 3 by 3 matrix. It becomes a 9 by 1 vector now, because each vector has a three entry, and there are three such vectors that you're stacking, so it's a 9 by 1 vector. So in general, if you have an NR cross NT matrix here, the vectorized version will become NR NT cross 1. Okay, so this is very important. Vectorization means take all the column vectors of the original matrix, stack it one below the other. That is called that operation is called vectorizing a matrix equation. Okay, so now you vectorize this all terms in the equation 4. So y of t, it is a matrix of size nr cross nt. So when you vectorize it, it becomes a nr cross nt, nr nt cross 1 vector. Okay, now w of t is basically the vectorized version of the product of these three matrices, and z of t is a vectorized version of the original filtered noise matrix in equation 4. Okay, now what is very important, how does w of t relate to each of the elements present in this three matrix product term in equation 4? Okay, you can show that this w of t can be written as some matrix A times gamma of t, where gamma of t is a vector of all the reflection coefficients, gamma 1, gamma 2, and so on till gamma p. Okay, it's a vector of the reflection coefficients of all the p targets, and this A matrix is now, you can show that that is the effective steering matrix. Okay, which is related by the two ANT and ANR matrices by the operator you see here a star. This star is called the Khatri-Rao product. Maybe I can ink it up. This star is called the Khatri-Rao product. Okay, so basically you can show that if there is a matrix AR times the gamma of t is a diagonal matrix. This AT Hermitian is basically a Hermitian is basically another matrix. Then you can show that the vectorized version of AT Hermitian gamma times AR, sorry, AR times gamma times AT. Okay, for now, assume it's transpose. Okay, you can show that this is equal to AT chronic Katri-Rao AR times the vec of gamma, where vec of gamma here is equal to small gamma of t. This gamma. Okay, this like just like how it is not the usual matrix. If you have a matrix A and if you have another matrix B, you just multiply A and B, you get one matrix AB, right? That is different. This is different. Katri Rao, you can Google and search in your free time today. You can search in Wikipedia. There's a Wikipedia page for it. It's called the Katri Rao product. I have made a mention of it here. So there's a separate paragraph for notations. So here it appears, Katri Rao product. Okay, it's a very useful product in simplifying the notations. You can take a look at it. So what I'm trying to say is this matrix A in itself combines all the 2p parameters. There are 2p parameters, right? So theta 1 comma phi 1 are the parameters for first target. Theta 2 phi 2 for the second target. Like that, theta p phi p is the direction of departure and direction of arrival for the ph target. So there are 2p parameters. All these 2p angles are hidden within this capital A matrix. Okay, so you can show that. So essentially, see this equation 5. This equation 5 is precisely the signal model that professor had done in class. This is basically the same as your y is equal to ax plus n model. You have now you recasted your problem into a problem for which the solutions are known to us. Okay, you have done this, nice matrix matched filtering, these nice things you have done, and you have nicely vectorized, only to so that you've brought your problem, or you've molded your problem to another problem for which the solution is already known. Okay. From here, I will use my conventional music type algorithms in order to solve the angles. That is the goal of this paper. Okay, that basically concludes our discussion on the signal model. Now let's jump into solution. How were the solutions attempted? Okay, now again, time frequency representations. Well, I do not want to touch upon time frequency representation in depth because it requires a lot more time. Also, not precisely the goal of this particular course. So let me skip this. But if you, anyways, I'll share this PDFs with all of you so you can take a read at it in your leisure. But all I want to tell is this one where am I going to use time frequency analysis in the solution? If you recall, okay, here it is. You see the equation 13. This is precisely the equation that professor also had written in the class that relates the autocorrelation matrix of the array output with respect to the autocorrelation matrix of the sources. Okay, so here R gamma gamma is the source, the autocorrelation of the source. Here source is like the target. Okay, so for example, C matrix, C equation, equation 5, what does it say? It says as if, so this matrix A is of size NR NT cross P, and this gamma of T is of size P cross 1. So we have casted the system as if it's a single array. There are P sources, and each source is sending sending a signal to the array, and the array has to estimate the direction of each of the P sources. It's just like that. It's just like that. It's as simple as that. So essentially, if you consider that kind of a system where there are P sources, this is exactly the equation that professor had written down in the class. Correct? Now, in this paper, what I have done is I have shown that this kind of a relation you can obtain using a matrix, something called STFD matrix. Okay, this is called an autocorrelation matrix. This DYY of T comma F is something called STFD, that is spatial time frequency distribution matrix. Okay, you need not know what that matrix is exactly. You can maybe read this short piece of text to understand. But what I'm trying to say is, you see, this matrix is better matrix because of one property, that it is a function of t and time and frequency both. So essentially, for every time and frequency point, you will get a different matrix. That's how you can improve the accuracy of your estimation of your angles, even when the source targets characteristics is non-stationary. Okay, this time frequency analysis also sometimes comes in the class of something called non-stationary signal processing, where the characteristics keep on changing, which necessitates the need for finding the spectral content in the signal repeatedly in time domain. So okay, so that is it. So basically, just take away that I'm going to use equation this dyy of t comma f in place of ryy. That is the only difference I'm going to do. I will not talk more about what is dyy. Okay. Okay. Now we will basically, this particular page is very important. It's very, very important. Now all of us know a very crucial, very important algorithm, namely music algorithm. Now in this paper, I have used another one algorithm in order to perform the direction estimation called ISPRIT. Okay, I will also quickly tell what the principle behind ISPRIT is. ISPRIT is like a music. It is another another algorithm like music. Okay, I'll quickly tell what the high level idea behind what ISPRIT does. Okay, so it's a new algorithm that I'm describing to all of you. It's called ISPRIT. So full form of ISPRIT is estimation of signal parameters via rotational invariance technique. Okay, so the first E stands for the estimation, the S here stands for the second S, parameters P stands for the third P, R stands for the fourth R, the invariance I stands for the fifth I, and T stands for the last T. Okay, so this is called estimation of signal parameters using rotational invariance technique. Okay, so the principle behind this is as follows. Okay, suppose you have an array. Okay, so the principle is very simple. Okay, suppose you have an array like this. There's an array here, and there are so many antennas. Let's say there are n antennas. Maybe I should draw it a little carefully because this diagram is important for this particular technique to understand. There are 1, 2, 3, 4, 5, 6, 7. No problem. Let's take n equal to 7. There are 7 antennas. There's a source here. Okay, it emits a signal, and the signal comes to every antenna. Okay, this signal comes to every antenna. It makes the same angle. Let's say the angle made by this source is theta1 at the array. Now the main principle behind Spirit, what it does is it will divide the entire array into two subarrays. So for example, this is called subarray 1. That is, it excludes the last element alone. Okay, exclude the signal contribution from the last last antenna. This is called subarray 1. Now 1 to 6 is subarray 1. Similarly, 2 to 7 is subarray 2. That is, in the two subarray, in each of the subarrays, discard the contribution from the end antennas in the respective subarrays. First subarray, discard the contribution from the last antenna. The second subarray, discard the signal output from the first antenna. Okay. Now it's very important to see the array vector corresponding to first subarray. I will call it as A1. So what is A1? Think about, okay, let's first write the overall array vector. Okay, overall array vector. That is, if you had not done the divisioning of the array into two subarrays, then you would have written the overall array vector would have been 1 e raised to minus j pi sine theta 1, e raised to minus j 2 pi sine theta 1, and so on till e raised to minus j 6 pi sine theta 1. Here specifically 6 because n is equal to 7, so n minus 1 is 6. Okay, if you had divided, so every element correspond to each antenna in the array. That is basically the way in which we construct the array response vector. But now if I divide both the arrays into two subarrays, then what happens is the array vectors corresponding to each of the subarray is obtained as follows. The first, okay, I should write down one more. E power, okay, let me write down completely, no problem. This is nothing but e power minus j 3 pi sine theta 1, e power minus j 4 pi sine theta 1, e power minus j 5 pi sine theta 1, and e power minus j 6 pi sine theta 1. Okay, this is basically entire array vector for this 7 element length array. It is basically the length is what, 7 cross 1. Now for the subarray, if I do a subarray, then the first 6 elements will be the A1, the array vector for first subarray. And this from second to the last will be A2, the array vector for second subarray. So this is first subarray. Okay. So now what is the difference between, no, this is called A2 and A1. What is the difference between A2 and A1? It's very important to see. You see the same array, the same array. I mean, I can, okay, let me write down A2. Let me write down A2. Okay, I will write down so that you see by yourself. Okay. A2 is nothing but e power minus j pi sine theta 1, e power minus j 2 pi sine theta 1, and so on till e power minus j 6 pi sine theta 1. Okay, it's a 6 cross 1 vector. Now I can write this vector as, just a minute. I can write this vector A2 as, take e power minus j pi sine theta 1 common. Okay, I can write this as 1 e power minus j pi sine theta 1, and so on till e power minus j 5 pi sine theta 1. But if you see, this vector is precisely A1. So I can basically combine, I can relate the array vectors of both the subarrays by just one complex number. I can, the A2 equal to e power minus j pi sine theta 1 of A1. Okay, so and you see this multiplier has the information about theta 1, which is the direction of arrival from the source. Okay, so this is basically essentially the notion of rotational invariance technique. So rotation here means, so this e power j theta is something like rotation. Okay, so I mean, you can think about it rotating a complex number. So even if you rotate the complex number, you will not lose the information in the signal. Okay, that's called the rotational invariance technique. Okay, so now if you collect like this, if you do for all the p targets, okay, now for p target case, okay, your A2 matrix can, which is defined as A21, A22, and so on till A2p. That is basically the subarray, the second subarray array vectors. So the second subarray constructed at all the p direction of data arrivals. And if you define matrix A1 is equal to A11, A12, and so on till A1p, that is the array vector corresponding to the first subarray for all the p sources. You can write your matrix A2 equal to A1 times another matrix phi, where this phi equal is of the form e power minus j pi sine theta 1, e power minus j pi sine theta 2. It's a diagonal matrix, and the last entry is e power minus j pi sine theta p, where theta 1 to theta p are the direction of arrival of all p sources. Okay, this is the important fact that you have to know, that A2 equal to A1 times phi. Okay, so once you know the matrix phi, you can just do. So suppose if x is equal to e power minus j pi sine theta 1, you can always find theta 1. How? just take log x, fine, equal to nothing but minus j pi sine theta 1. Now take, this means that 1 by j times log 1 by x equal to pi sine theta 1, fine. And then you can take 1 by j pi log 1 by x equal to sine theta 1. In order to, since it should be a real number, take magnitude on both sides. And theta 1 is essentially sine inverse of 1 by pi log 1 by x. So once you know the diagonal entries, you can always find what is the respective theta i's. That is, it's just a one-to-one relation. But if you somehow know the matrix phi, then I know the direction of arrival or the angle information of all the p targets. This is precisely the principle of Esprit. So let me quickly write down. Okay, now we have understood the system, how what Esprit does. So now recall that the true array vectors, that is, if there are p targets in the environment, the array vectors corresponding to these, the angle information of all these p targets, the true array vectors span the signal space. The true array vectors span the signal space. Correct? If you remember, we divided the entire signal subspace. We divided the entire vector space into two classes of something called the signal subspace and the noise subspace. And we told that the space spanned by all the array vectors corresponding to the true angle of arrival will span the signal space. All the other vectors, the span of other vectors will be in the noise subspace. Fine. This is what we saw. This professor had discussed in class. That means I can always write the signal subspace U S equal to some A, which is my true array vector matrix collection of all the vectors, times some transformation matrix F. Some transformation, it's an invertible transformation. Or okay, it's some transformation. Need not be invertible, but for which pseudo inverse exists without any problem at least. It's some transformation matrix. You can always write US is equal to A times F. Okay. Now see this. How did we obtain A1? A1 is nothing but you have discarded the last entry of your vector A. That is your A1. And A2 is nothing but you have discarded the first entry of the vector A. That is called A2. You can show that equivalently you can obtain. Okay, so what did we obtain? And we had A2 is equal to A1 times phi. This is what we obtained here. This let's call equation 1. Fine. Then you can write this as some matrix J times A1. This is called J2 times A equal to J1 times A times phi, where A is basically the true array matrix, but J2 and J1 are the matrices which perform the operation of discarding the first element or the last element. So J1 and J2 are called selection matrices. Okay, so we have the function that J2 of A is equal to J1 of A times phi. Now, I know from equation 2, I can write this as J2 of US times F inverse is equal to J1 of US F inverse phi. So US is equal to A F inverse, which means A is equal to US times F. Sorry, US is equal to A into F by equation 2, which means A is equal to US into F inverse. That is what I'm just substituting for the value of A here. Okay. Then what you can show is this is same as now. I can show that J2 of US equal to J1 of US into F inverse into phi into F. Basically what it is, I post multiplied by F on both sides, and this will become identity. So J2 into US is equal to J1 times US times F inverse phi F. Okay, but J2 US you can call that as US2. That is the signal subspace spanned by the first subarray. This is the signal subspace spanned by the second subarray. This is some other matrix H. Okay, some other matrix H. Now H is equal to what? F inverse phi F. Okay, this is a diagonal matrix. What it contains the angular information of all the P sources. Okay. Therefore, I don't know how many of you know. There is this if given this, what does it mean? H into F times H is equal to phi times F, or H into Fi equal to phi into Fi, where Fi is the ith column of F. Now, can anyone tell me what does this equation remind you of? H into Fi is equal to phi times Fi, where phi is the ith diagonal element of the matrix phi. What does this equation remind you of? Yes, can anyone tell me?
We have gone through one such a pattern in the
Yeah,
course.
you remember this?
Yeah.
Do you remember this?
Yes, sir. This
What
is
is
eigen
correct? So
matrix.
think your H is equal to A. Your Fi is one column vector like X. The same Fi is X. Lambda is equal to phi. Correct? Phi. Is this
But this
fine?
H F inverse phi F, I think we have some A gamma A something like that.
Ha
We
ha
have.
ha. That was different. No, that is different. This if you remember, this is also like eigenvalue decomposition. It's like eigenvalue decomposition with eigenvalues along the diagonals of phi. I will erase this. You remember this? It's nothing but it looks like the eigenvalue decomposition. I will write it. Eigenvalue decomposition of the matrix H with eigenvalues along diagonal of the matrix phi and eigenvectors as columns of matrix F. Do you agree with this?
Yeah, something, yes, we have gone through some.
Yeah, that means your your diagonal elements of phi, okay, of H, sorry, diagonal elements of phi equal to eigenvalues of H. So if you somehow compute the eigenvalues of H, that will give me the entries of all the diagonal elements of phi, and exactly the diagonal elements of the matrix phi contain the angular information of all the p sources. Correct? Let's see here. See the diagonal. This is basically phi. It contains theta 1, theta 2, and so on till theta t. You can precisely do this. Okay, you can precisely do this kind of a transformation where x is basically phi, a diagonal element of the matrix phi. Okay, so the goal is then somehow find the eigenvalues of H. But how is H in turn defined? It's defined as this US2 is equal to US1 times H, or H is nothing but US 2 times US1 pseudo inverse. If the inverse exists, let it exist. If not, just define pseudo inverse. Okay, so essentially what it says is somehow find the matrix US2 the times US1 pseudo, that is the signal subspace spanned by the second subarray times the pseudo inverse of the basis vectors of signal subspace spanned by the first subarray. If you find this matrix H, then do the eigenvalue decomposition of H and find the eigenvalues. The eigenvalues will then tell you the information of all the P angular values. Okay, this is the principle behind Esprit. So you see, in music, we try to find out the noise subspace, and we utilize the property that signal space and noise subspace are orthogonal to each other. So essentially, we computed UN. If you remember UN, that is the basis for the noise subspace. But in Esprit, we don't care about the noise space at all. We only play with the signal space of different subarrays. But in music, we don't divide into subarrays. In Esprit, we divide into subarrays and solve the same problem in a different way. Okay, so this is basically the principle of Esprit. Okay, so in this paper, what I precisely do is I do both Esprit and music. Okay, specifically what I do is there are two p parameters, right? Theta 1, theta 2, and so on till theta p. then phi1, phi2, and so on till phi p. Okay, these thetas denote, see this picture again. The theta denotes the direction of departure, and phi denotes the direction of arrival. This is a kth target, so it is theta k and phi k. Okay, so what I will do is I will use Esprit technique to find out this angle theta 1 through theta p, and I will use the information of all these DODs, and then in estimating this angle direction of arrival at the receiver array using music. I will use both Esprit and music in order to find all the 2p parameters. Okay, and I call this particular algorithm as a joint DOD-DO estimation because I use Esprit first to estimate all the p direction of DOD departures and use the estimated value somehow, as extra information in order to estimate all my angle DOAs using music algorithm. Okay, maybe you can. I have whatever I have told you. See, he's here. For example, this is precisely your US1 pseudo. Okay, so I've explained all of it here in this paper, but I recommend you to go through the paper once you get some free time. Okay, so essentially, I use music in order to recover all my theta case. Okay, once I use music, then I use Esprit to estimate all my theta case. Then I use music to estimate all my phi case. Okay, if you remember music cost function, we construct something like 1 by un times a of phi norm square, and then compute this function as a function of phi. You do phi, and then it peaks at some point. Wherever the peak comes, that is your estimated DOA. Okay, here I derive the music cost function as similar to equation 18. Okay, there is this product. This product is called Kronecker product. I mean, it's called Kronecker product. Okay, you can just go over the outline of this paper in your free time, but if you don't understand Kronecker product, don't worry. Kronecker product is also a product similar to Cartesian. It also has its own Wikipedia page. You can go and Google over it. So the high level idea is that I use both Esprit and music jointly in order to estimate all my direction of departure and direction of arrival. Okay, let me this is the algorithm one, which summarizes all the entire algorithm. So the first step, so here from, you see, I write module 1. It does the construction of the STFD matrix, of the spatial time frequency distribution matrix. That is done from lines 3 to lines 12. Okay, then I do something called, then I do the eigen decomposition, because because you remember I need to first find out my signal space and signal space. You remember, because I need to construct this. Okay, where is this? You see, I need to construct this H matrix. Where is that H matrix? I need to construct this H matrix. For that, I need to know my signal space and noise spaces, right? For that, I need to do eigenvalue decomposition and take the eigenvectors corresponding to P sources. Again, I assume that I know the value of P a priori. Okay, so I do the eigenvalue decomposition here. Then I do Esprit algorithm. I use the word TF Esprit because to tell that I'm using a time frequency based matrix to do Esprit. So I give the new name to this method called TF Esprit. Okay, time frequency Esprit. The same algorithm. So first I find the matrix Q. So you remember I wrote US is equal to A times F. Okay, so the matrix F is playing the role of Q here. Okay, then I define the subarray matrix A1 and A2. Then I basically define my the signal subspace corresponding to the first subarray and second subarray as US1 and US2. Then I found out my H matrix that I described using this matrix psi here, and then compute the eigenvalues of psi, which will be this zeta I, and then use this zeta I, do the inverse operation, and find my Esprit. Find my direction of departure at towards all the P targets. Now, once I use all the DOD estimate, use these in the cost function. See, this cost function is very similar to your music cost function, which we had seen in class. Okay, so I iterate this particular cost function with respect to all the phi and check the peaks. So you will get P peaks, phi1 hat, phi2 hat, and so on till phi hat p. You will get p such peaks, and you can then find out the direction of arrival for all the p targets. So this is how you compute both the direction of departure and the direction of arrival of all the p targets in the system. Okay, so I have done some. I have also listed the complexity analysis. So it's a very big algorithm, right? So every step will have its own complexity. What is the number of multiplications and additions you may want to incur? So I've indicated all of them in this particular table, and I have compared what is the use in terms of complexity. How well can you reduce the complexity of the algorithm compared to the autocorrelation based method? Basically, instead of using an STFD matrix, if I had used an autocorrelation matrix RYY, okay. So by using an STFD, how can I cut down the complexity? Can I get a low complexity method? And so I have discussed that in this particular paragraph. And then I have also discussed the performance guarantee. So how well can this algorithm estimate the true values with small error as possible? So in literature, again in estimation theory, for those people who know, there's something called Kramer-Rao lower bound. Okay, it gives a lower bound on how small the error can be. Okay, and if you can design an estimator such that you can achieve that bound, then that is the best you can do. You cannot achieve an error, the error in estimation, which is smaller than this bound. Okay, so what it is for that, the Kramer-Rao lower bound depends on the system model. Okay. So for this system, I have derived the Kramer-Rao lower bound, and I have compared the error achieved by this algorithm, this estimation algorithm, against the bound that I have derived here. Okay, and that basically comprises the numerical result. So these two figures tell the use of using a time frequency representation. Okay, then this figure is exactly the thing that I was talking about. So RMSE there's a RMSE term on the y-axis which denotes like root mean square error. On the x-axis I have SNR. Okay, this violet curve represents the Kramer-Rao lower bound CRLB. The red curve represents the error that I achieve, error of your DOE, the estimation of angle using Esperit, and this blue curve represents the error of estimating the angle using non-TF, that is a regular autocorrelation based approach. You see the error in this, the red curve lies below the blue curve, which means the proposed algorithm is doing better. Okay, and this is for DOD estimation. This is for DOA estimation. You see that after some point, both again here the blue curve lies above. The error in your conventional approaches will be little more than the error in your time frequency approach. And after some point with high SNR, all of them converge to the CRLB, which is a wild curve, which means our proposed algorithms are doing better. Okay, and I've done some more performance analysis in terms of okay, if there are two targets which are present close by, what is the resolvability power of the algorithm? Because if there are two targets which are closely placed, then my estimation algorithm should be able to detect both of these targets and give their angular information correctly. It should not confuse one angle for the other. Okay, so that kind of a performance analysis also I've done, and some more performance analysis in terms of detection probability. What is the probability with which I'm able to detect the angles correctly? Such kind of analysis are there in this paper. Okay, so that basically brings me to the end of this particular paper. Okay, are there any questions in this paper?
So it's basically the detection of or better detection of the target.
Yes, correct. You can associate the angle of the direction of departure and direction of arrival as it's a two parameter for every target. So every target you can think about it as having a parameterized by two values as a vector. So it's a 2x1 vector, and you want to find that this 2x1 vector, estimate the 2x1 vector for every target.
2x1 for a
Yeah, direction of departure and direction of arrival for every target. So it's like theta 1, theta 1, phi 1 is associated with the first target. So it's a it's a two variable. So you can associate that as a 2x1 vector.
Okay. Basically, in the course we have, I think two things. One maybe agent value decomposition or singular value decomposition. So, such a application, any application of that here, or it is
Here also you see. Yeah. So basically here also you see this particular from this lines 13 to lines 18. Exactly you do eigenvalue decomposition of your STFD matrices to compute the basis for signal space and noise space. You have to do eigenvalue decomposition. So again, my suggestion is go back to the music lectures. I mean, music lecture means that multiple signal classification lectures. You same steps you will have to do there. Here also, I'm doing the same steps. The main difference between this work and that work, the professor's lecture was there. Every target was associated with one angle, direction of arrival. That's all. But here, every target is associated with two angles, direction of departure and direction of arrival. That is the main difference between this work and what was discussed in class. Okay. Now again a side point. Suppose if I were to consider a monostatic radar. A monostatic radar means, see here, both the transmitter and receiver are at the same place, which means the direction of departure will be same as direction of arrival. Correct? So then for this monostatic radar problem, you can cast your problem into whatever the professor had discussed in the class. Correct? So then it's just, you will not have two different parameters for the same problem. You will have just one for one target. You will just have one parameter for every target, which is same as what professor had discussed in class. Only because it's a bistatic radar where the transmitter and receivers are separated. Okay. Only because they are separated in space, you are having two different angles for every target. Okay. So there's a chart question which says, can you please tell me the practical implementation of this algorithm? Yeah, that's a good question. So see that it depends on the complexity. So one would want to understand whether can I use music and Esprit, okay, for this. So this is one particular solution that you can attempt. But if you see, I have still this particular work are not completely. It doesn't take even. There are more practical assumptions you need to take into. For example, there is something called coherent target scenario where there are two targets which can be correlated with each other. If that is the case, you need to do much more than what you are doing in this paper. And you have talked about what resolution is obtained. Yes, that's a very good question. So I have also done this work. So you see here there is something called resolvability and at two different SNRs. So I have done this, and you can read this paragraph. I quite don't remember, but this paper does contain results about what is the best resolution that you can achieve. So essentially one high level answer that I would give is resolution in some sense depends on the number of antennas that you use in the system. If you want a very better and better resolution, meaning that there are two targets which are very, very closely placed, let's say they differ by 0.1 degrees in their angles, then you may want to have large number of antennas in order to distinguish these two targets as two different targets. But if you, let's say you have only two or three antennas, then it's possible that the main lobe of the antenna, within the main lobe, both the targets will come. So the system, the receiver cannot resolve these two targets as two different targets. But if you want to resolve these two different targets, you should have a very large array. Then what happens is your main lobe will become narrower and narrower. That in one particular, the main lobe in one angle will not contain both the targets. So it will be able to resolve the two targets separately as two different targets. So in some sense, the resolution is not something that is only algorithmic dependent. It also depends on the physical parameters like the number of antennas that you choose and so on. Okay, but for this particular measurements, I don't quite remember. I have to read this particular paragraph. You can take a look at this paragraph in your leisure. Yeah, can you please share that? Of course, yes. So one way to do is, so I will definitely upload these on NPTEL shared folder. The other way is you can take a note of this paper. If you Google this paper, this is actually my paper that I did as a part of my BTech project. If you just take the title of this paper and put it on Google, you will get this paper. Okay, so is it fine? Okay, so actually I planned more, but I think I cannot do more. Okay, so this is basically the second piece of work that I would like to share. But it's 7:30 p.m. What I will do is I will let's not go for break today. I will finish the class 10 minutes before 8 o'clock, so that we basically postpone the break till 7 to 7:50. Okay, so this is my other piece of work, which is along the lines of the same. It's exactly the solution is exactly the same, but in a casted for a different problem. Okay, this basically came out is one of my initial works in my PhD actually. Okay, so this paper is titled Cascaded Channel Estimation for Distributed IRS Aided Millimeter Wave Massive MIMO Systems. Okay, so there are some motivations and so on and so forth, but let me jump into system model. What is this system that I'm considering is exactly given in figure 1. Okay, so there is a base station, there is a user. Okay, and they want to communicate with each other. And if you remember from previous classes, one fundamental thing that you need to do before even doing the communication is you need to know the channels between the base station and the user. Okay, and precise and I work on something called intelligent reflecting surfaces for wireless com, and that is abbreviated as IRS. Okay, so you can think about an IRS as something like this. So what it does is the base station sends. So here I assume uplink, meaning that I send the signal from the user to the base station. So what happens is when the user sends the signal, it will go and hit the IRS. It's a reflecting surface, and then it will go back to the base station. Okay, like that I have k such IRSs which are distributed in the environment. Okay, so this is IRS1, then IRS2, k minus 1, IRSk. There are k such IRSs which are distributed in the distributed in the environment. Okay, and each IRS has LK elements. The kth IRS, for example, first IRS has L1 elements. Each element you can think about it as for example, as an electronic a circuit. Okay, which can give its own reflection coefficient. Okay, for example, the picture has 9 elements. This will give a reflection coefficient of e power j theta 1. This will give e power j theta 2. This will give e power j theta 3. Like that, you can get e power j theta 9 till e power j theta 9. So there are 9 reflection coefficients if L1 equal to 9. Okay, so basically the use of an IRS. So what IRS does is it will try to reflect the signals in a desired direction so that the overall channel seen by the base station is improved. Okay, so maybe quickly I should give you an overview of what really this is about. Okay, so an IRS, so that you understand what an IRS does. Okay, there is a, let's say, simple scenario. There's a base station, there's a base station tower here, there's a user here. Okay, and there is an IRS in the environment somewhere here. Okay, so each element can reflect the signal to the user. Okay, so then the goal of an IRS is, so let's say this is H1, this is H2. There's also, in addition, there's a direct channel between HT and base station and the user. It's called HD. Okay, there are n elements. Let's say there are n elements. For a moment, you consider one antenna at the base station and one antenna at the user. Okay, so then you can show that the overall channel seen by the user is equal to sum of both the channels HD and through every IRS element. I is equal to 1 to n. Call this as H1 and call this as G1. G1. Okay, that is the, okay. Maybe I should not confuse. Let me do this properly. Channel between the base station and the first IRS element is H1. Channel between the first IRS element and the user is G1. Okay, similarly, channel between base station and the second IRS element is H2. Channel between the second IRS element and the user is G2. Okay, similarly till Hn and Gn. Okay, so the overall channel seen by the user is given as sum of Hd and sum over I is equal to 1 to n Hi times Gi. It's a product because it's a cascade effect. It's product times the reflection coefficient of the IRS, which is e power j theta I. Okay, so in traditional wireless communication, the goal is basically to maximize mod of h square. Why? Because if you remember from third or fourth lecture, we saw that the rate that you can give is the data rate that you can achieve with the user is something given as b times log base 2 1 plus mod h square times p by sigma square, where p is the power with which the transmitter transmits, sigma square is the noise variance, and d is the total bandwidth. Okay, this is measured as mbps or bps or kbps or whatever it is. Okay, c is mod h square is the channel quality. If mod h square is more and more, I'm going to get better and better rate. Okay, so basically I want to improve the signal channel strength. Mod h square represents the channel quality, the channel strength. So what IRS does is you need to design the IRS. The goodness about IRS is you can control the reflection coefficient of every element independently and individually. Okay, so the goal is design your theta I such that mod of h square is maximized. Okay, this will happen if the terms hd, h1 g1 e power j theta 1, h2 g2 e power j theta 2, and so on till hn gn e power j theta n, all of them add in a constructive interference manner. Okay, all of them will add constructive or a coherent manner. Okay, if you remember constructive interference and destructive interference, constructive means all of them should add in the same phase. So if you remember H is a complex number. So each of them will have its own complex number. But somehow you design a theta 1, theta 2, and so on theta n such that this sum, all of these individual sum will add in same phase so that the H is as maximum as possible. Okay, that is basically the fundamental design criterion behind using an intelligent reflecting surface in an environment. Why it's called intelligent reflecting? Because you can choose how you want the IRS to reflect. You can choose your reflection coefficient theta I. That's why it's called an intelligent reflecting surface. It's intelligently reflecting. That's what it's called, because you can choose your theta I. Okay. So again, if you see you by now you would have guessed the choice of theta I depends on what are the values of HD, HI, GI. That means the knowledge of what reflection coefficient you're going to choose the IRS depends on the channels, this channel that exists between the base station IRS and user, and base station user. HD, H1, H2, HN, G1, G2, and all these, you should know the value of all these values so that you get to know, you can come up with the optimal theta I in order to maximize mod of H square. Okay, so that basically tells that you need to know the channel state information, and that is the goal of this paper, to perform channel estimation of your of all the links in the system. Okay, so I have to estimate. So now I'm considering a multiple antenna at the base station and the user. The picture was this for single antenna. So this considers n antennas as the user and m antennas at the base station, and there are multiple such IRSs, each with LK elements, or L1 for the IRS1 and so on. Okay, so now I'm going to describe the system model. You see equation 1 basically tells the channel between the user and the kth IRS. Let's say that there's some arbitrary kth IRS. Okay, the links were the kth IRS. This H2K represents the channel between user and IRSK. Okay, now when the signal propagates from the user to the kth IRS, this signal can undergo multipath. That is precisely how the wireless channels are. So for example, what I'm saying is, this is how it happens. So if there is a base station here, there is an IRS here, there's a user here. It's after all air, right? So what happens is the channel between user and IRS could be something like this. It can go via multiple paths. Okay, so because it's a wireless channel, you don't get to control this channel. So it has a multi-path. Each will have its own angle of departure from the user and own angle of arrival at the IRS. I assume that there are some number of paths. Similarly, the channel between IRS and base station will also have some number of paths. Okay. These are what are called multi-paths. Okay, this is inherent to any wireless channel. So here Um, that is how I model my equation. The equation 1, I model that there are nk parts between the user and the kth iris. Okay, see, nk represents the number of spatial parts between the user and the kth iris. And this is very simple. I mean, same as what I described in the radar problem. A times lk, alk represents the array vector at the iris, and an represents the array vector at the user, and the corresponding angle of departure and angle of arrival is given by omega and phi. So omega ik represents the angle of arrival at the kth iris via the ith path. Phi ik represents the angle of arrival at the angle of departure at the user to the kth iris via the ith path. Okay, and similarly, for simplicity, I assume that there's only one path between the iris and the base station. That is, I have substantiated that with some the deployment strategy. You should deploy your iris such that there is a strong line of sight component between the iris and the base station, so that every other path will have very low energy. Okay, so that you can ignore them. Okay, so that is basically, so there's only one part, so that I don't have any summation. Okay, so second equation is the channel between the kth iris and the base station. Okay, again, accordingly you will define your array vector. Similarly, you have a direct component also. Okay, so you can show that your effective channel is given by equation 4. Okay, HD is basically the channel between the user and the base station via the direct path, while H1K is the channel between the channel between the IRS and the base station. Theta K is the diagonal matrix having the reflection coefficients of all the IRS elements at the kth IRS, and H2K represents the channel between the user and the kth IRS. Okay, you can write this as HD plus G. Okay, now what I'm doing is, now I'm going to describe the algorithm for channel estimation, meaning that you need to estimate this HK. Okay, for now I assume that HD is known. If I know HD, I can always do H minus HD is equal to H hat equal to G. I'm only interested in understanding the channel through the IRS, not HD. Somehow I know that HD is already known. Okay, that's why I'm interested only in the channels through the IRS. That's why this paper is titled Cascaded Channel Estimation. It's cascaded through the IRS. I'm not interested in the channel in the direct path. Okay, and it's called millimeter wave massive MIMO. Why? Okay, let me tell. Distributed IRS, because there are so many multiple IRSs which are distributed in the environment. It's called millimeter wave massive MIMO. Massive MIMO because the number of antennas and the number of antennas the base station I consider M to be much larger than 1. Then this is called massive MIMO regime. And millimeter wave, because only in millimeter wave regime can you model the angles like this. Okay, because what happens is, if you consider sub 6 gigahertz, that is millimeter wave, is very high frequency bands. In low frequency bands, what happens is this NK number of parts become very large. Okay, there are so many multi-parts. There's a tool called central limit theorem, which will tell that as this number of multi-parts get very large, the entire channel will become something called the Gaussian channel or the well-known Rayleigh channel. For Rayleigh channels, equation 1 and 2 are not the correct way to model your channels. Okay? That's why it's only in millimeter wave these kind of channels are a valid channel models. Okay, now what I do is basically I do see equation 5 is basically the received uplink pilot signal. Okay, from one transmission. Then what I do is I subtract the contribution from direct path. Okay, hence I subtract the direct signal to obtain this y is equal to gx plus n dash, where x is the transmitted signal at the user, g is the channel from the user to the base station via the ARS only. I ignore the direct path. And what I do is, again, like how I told for radar case, I should transmit as many pilots as there are number of users in the system. Now, as there are number of transmitter antennas. Okay, under that condition, I can do this kind of a matched filtering. Where is that? To ensure orthogonality of the pilot sequences, I can do matched filtering. Okay, that is by post multiplying or received by your transmit waveform x admission. Okay, then I can get this equation 8. Z is equal to G plus N. Now what I do, I analyze my equation G a bit. I get something like this of 9 form. Okay, all these are simple algebraic manipulations. Okay, then I get this equation 9. This G can be written as something like equation 12. AM tilde times gamma, which is a diagonal matrix, times AN transpose. Okay, so I can write my effective channel as Z is equal to AM tilde times gamma times AM transpose plus noise. Okay, now if you recollect, this is the channel is now exactly how we had done for the radar case. Okay, so now you can vectorize the snapshot of observation. You will get this equation: Z is equal to E effective times gamma plus N. Okay. Now for this system, use the same solution of joint, aspirate, and music which I had described in the previous work, and you can obtain all these direction of arrival information. Omega ik, phi ik, all these are the parameters which you want to estimate. All of them can be estimated using joint, music, and aspirate algorithm. And once you estimate all the angles, see this, there is something called beta k, alpha ik. You see this? Do you see this? Alpha ik, beta k, all these zeta k. These are the complex channel coefficients, which represents many other factors. They can be estimated by least squares. Similar to, if you remember what we did is, once we estimate all the angles, you only choose those array vectors corresponding to the true angles and do a least square solution in order to estimate all these complex channel gains. That is precisely the way I will do. See here, I do this in equation 15. I will estimate all my channel path gain coefficients gamma using equation by including least squares. Once I know all the angles of all the paths, then you can maybe, I won't, in the interest of time, I'll just mention that if you use this kind of an algorithm, potentially I have told how many antennas do you need in the user and the receiver so that this algorithm will work effectively. So remark one says what is the required number of antennas, the base station, and the user. The second second remark describes the number of pilot transmission. That is, how many pilot transmission do you need to do, okay, so that you can get a good reasonable estimate of this particular the channels in the system. Okay, these are two remarks, and I've done some numerical experiments here. For example, you see figure 2 here. Figure 2 basically represents the comparison of this particular algorithm versus SOMP. SOMP is an algorithm. So SOMP is, already all of you know. See, if you remove S here, it's just OMP, which all of you have seen, orthogonal matching pursuit. But SOMP is a variant of orthogonal matching pursuit. That's some called simultaneous orthogonal matching pursuit, which is used to solve sparse recovery problems, which arises in blocks. It's called block sparse recovery problems. Okay, so essentially, it's a compressed sensing based technique to estimate the channel. Okay, you can always pose this problem as a compressed sensing problem. If you remember, we had posed our direction of arrival estimation as a compressed sensing problem long back as a sparse recovery problem. Similarly, you can pose this problem also has a compressed sensing problem, and you can solve for the channels. Now, this particular plot shows that all the proposed solution using the proposed curve is denoted by the solid lines. Okay, the error of the solid lines keep on reducing with SNR, while you see the dotted lines represent the error with the channel estimation error using compressed sensing techniques based solution. So K here represent number of IRSs. So you see that error is flooring at just 10 power 0, which means as K increases, that means the number of IRSs increases. The error in estimating the channel using compressed sensing keeps degrading, whereas the proposed solution will not degrade. It is robust to the number of IRSs. Okay. Like that, and I'm told with respect number of pilot transmission, how does the proposed algorithm compare with the existing algorithms? Same with compressed sensing. And this is our favorite, music spectrum to say how accurate the algorithm can predict the angles, and some more results. If suppose the number of parts here, number of parts is like the number of targets, number of sources. If that is not known a priori, then what can we do to know that number a priori, and so on and so forth. And that basically is precisely the paper is about. Okay, so this is all I have for today. I had one more paper, but I think this is enough for today. So are there any questions? Okay. There's a chart exam related. I only have the information that it's going to be an online exam. More than that, I do not know exactly on how the questions will be based on. Not sure. You can try to ask maybe in the discussion forum. There's a discussion forum, right? You can try to ask there. Maybe see if you can get some inputs there. I'm not sure about it actually. Okay, so I think there are no questions. So yeah, so it's been then okay. So are there any questions?
Okay, so yeah. Overall, I think it added all the sessions added uh, some more insights, and I think for further into research or into the application of application into our own space, maybe for me it's 5G work related. Maybe we can get back, or we can get in touch with you.
Sure, yeah. So yeah, any comments from others? Let me stop recording maybe.